All right, so today we'll finish up section 4.2, looking at some more graphs, except we're going to look at a different, kind of a different category. Okay, this is what we did yesterday. Okay, so you don't really have to write that down, I'm just summarizing what we did. So we looked at graphs where the degree of the numerator was always less than or equal to the degree of the denominator. If the degrees are, if it's less than, okay, if the degree of the denominator is less than, you always get a horizontal asymptote at 0. If the degrees are equal, you still get a horizontal asymptote, but it's not at 0. It could be above or below 0. When we make it one step, a little, like the next step would be, well, what if the degree in the denominator was bigger? Numerator was bigger. Okay. And that's what we're going to look at today. So now the degree in the top is going to be bigger than what's in the bottom. And here, how bad the asymptote gets depends on how far apart the degree in the top and the bottom are. So like, if you look at one like this, the top is a degree 3, the bottom is a degree 1. That's a difference of a degree 2. If you look at this one, the top, same idea there. Here, this one, the top is a degree 3, the bottom is a degree 2. That's a difference of degree 1. That's going to be an easier one to sketch than one like that. Okay. The further apart the degrees, the worse the asymptote is, or more complex it is. All right, so any question between the difference in what we did yesterday and then what we're looking at today? Degree in the numerator is going to be bigger, that's all. And when the degree in the numerator is bigger, there's something new that we can find. And it's called the end behavior asymptote. Okay, so suppose we have some polynomial. Call those h of x and g of x, and we're going to divide them. And we're going to assume that h of x has a higher degree than g of x. All right, so again, suppose h of x and g of x are polynomials. You're going to divide them. And when you divide them, you're going to get a quotient and a remainder. Okay, just like always. So q of x would be your quotient. R of x is your remainder. And remember how you can write your answer. Quotient plus remainder over divisor. But that's how you could check your answer. If your quotient plus your remainder over your divisor equals what was in the top, equals your numerator, then you did it correct. Okay. Kind of like if we did, let's say, 5 divided by 3. Quotient would be 1. What's the remainder?
2/3.
So remainders are non-fractions.
Just the decimal point.
2, right? So when you divide 5 by 3, 5 goes into 3 once, remainder 2. If you write it the way you would with long division. Any question on that? Now, if you write it like this, 5 should equal your quotient plus, let's see, your remainder, which is 2, over, let's see, hold on, let me fix this. So, f of x, that was what I got when I divided. So, that would be 5/3. Okay, so I got 5/3 as the answer when I did the division problem. And now my quotient was 1. And my remainder was 2. And what did I divide by originally? 3. So if that works, then I did it correct, okay, to check my answer. Is 5/3 equal to 1 2/3? Yeah. So in this case, f of x equals my quotient plus my remainder over my divisor. Well, This part right here, the quotient is all we really care about. Right? We don't really care about the part on the end. The quotient is your end behavior asymptote. So in other words, when you're finding the end behavior asymptote, you're not doing anything new. You're doing the same thing we've always done, long division or synthetic, either way. But we're just calling the quotient the end behavior asymptote. Okay, and I'll abbreviate it EBA from now on. Okay. So any questions on how to calculate the EBA? Okay, let's try it on this one. Now, before I even do it, they're asking me to find the quotient, the remainder, and the EBA. What's the difference between the quotient and the EBA? You think they know? What's the difference between the quotient and the EBA? Yeah? Nothing. The same thing. The quotient is the EBA. So when they ask you to find the quotient, that's also the EBA. So really, they're only asking you for two things here. Right. Could we do this one as synthetic if we wanted to? Can we always use synthetic? What has to be in the problem to use synthetic? How do you know when you can use it? Abby?
The denominator has to be linear.
Yeah, the denominator has to be linear. Perfect. Okay, so on this problem, we could do synthetic. But let's do it as long division because I'm going to give you one where you have to do long division in a little bit. Okay, now when I put what's under that symbol, what do I have to be careful about before I just start writing it down? Yep.
You have to remember to put the things that are missing, like the x's.
Yeah, I got to put in any zeros for anything I'm missing. So it's 2x cubed minus 4x squared plus 0x plus 3. Okay, Tyler, what's 2x cubed divided by x?
2x squared.
Yep, 2x squared. Multiply it out. 2x cubed minus 4x squared. And subtract. 2x cubed are gone. Negative 4x squared minus 4x squared. That's gone too. Okay, so now we would bring down the next term. What's 0x divided by x? Dan, what's 0x divided by x?
0.
Just 0. So it's just plus 0. Now we're basically done at this point, but if you want to keep going, because they do want the remainder, we do need to finish it up. So 0 times x is 0x. 0 times negative 2 is a negative 2. And you're subtracting. If you want to bring down the 3 at the same time, or you can just leave it up above and look at it, but just remember you have a plus 3. Okay. So 0 minus 0 is gone. Whoops, I'm sorry. 0 times negative 2.
Yeah, okay.
0. Same thing I did last time. And now let's finish it up. What's 3 minus negative 0? Abby? 3. So that's my remainder. Okay, so let's write everything down. Quotient? How about, Alyssa, what's my quotient?
2x squared.
Yeah, you don't even really need to put plus 0, it's just 2x squared. Chantel, what's my end behavior asymptote?
2x squared.
Same thing. And my remainder, in this case, is 3. Right, so I want to think about writing it the way we had with that formula on the other page, and look at what happens to the remainder part, okay, the part that has the remainder in it. So let's write quotient plus remainder over divisor. So quotient plus remainder over divisor, x minus 2. I want to look at what's happening to that part. As x gets bigger and bigger and bigger, what happens to that fraction that I just circled? Yeah.
It approaches 0.
It approaches 0. So that's why when we're doing the end behavior asymptote, this part is insignificant. You know, if x was a million, you'd have 3 divided by 999,998. It's basically 0. Okay. Now when x is small, like say x was 1, then you have 3 divided by 1 minus 2 is -1. Then you get a much bigger number. But the point is we're looking at what happens as x approaches infinity. Okay, that part becomes insignificant. So this part approaches 0. Okay, that's what I want you to see. And that's why we don't care about that. All we care about is that. All right, so a couple important points. We're going to come back to that problem. We're going to use that end behavior asymptote to make a sketch right after we do this. So there's a difference between the end behavior model and the end behavior asymptote. Can someone remind me about the second one? How do we get the end behavior asymptote? That's what we just did. Felipe?
Find the quotient.
You find the quotient after doing division, either long division or synthetic. That's the EBA. Now, how do you do the EBM? That's a little easier. You don't have to use long division or synthetic division. That's what we did yesterday. Yep, Taylor's?
Just divide the two leading things. The first term.
Yeah, you just take the highest degree term in the top, divide by the highest degree term in the bottom. That's your end behavior model. Okay, end behavior asymptote doesn't exist for the kinds of problems we did yesterday. There is no such thing. So sometimes the EBM and EBA are the same. Like if we went back to this last problem and I asked you to find the EBM would be 2x cubed divided by x, which is the same as the EBA in this case. But sometimes the EBA and EBM are different. Sometimes they're the same. Kind of depends on the problem. Now, for the kinds of problems we did yesterday, if the degree of the numerator was less than or equal to the degree of the denominator, okay, I'm not talking about the vertical asymptotes, but I'm talking about the other ones. What were the other asymptotes that we had yesterday besides vertical? Yeah?
Horizontal.
We had horizontal. So I'm going to be even more specific than straight line and say horizontal. Actually, I think I already have that. Okay, we also have vertical, but vertical as well. But really, I'm not focusing on the vertical because you have vertical in the ones we did yesterday, you're going to have vertical in the ones we do today. I want to focus on the horizontal ones. So if the degree of the numerator is less than the degree of the denominator, you'll definitely have horizontal asymptotes. You'll also have vertical ones. But if the degree in the numerator is bigger, your asymptotes can be curved. Specifically, the curve is going to take the place of the horizontal. You could still have vertical. Those aren't going to go away. Okay, so you still have vertical, but the asymptotes can now be curved. And those would take the place of having a horizontal. Okay, and the hardest type of curved asymptote I'm going to give you today is a parabolic asymptote, so degree 2, and it's the one we just found. Technically, you could have any degree. Okay, if the degree on the top was a degree 4 and the one in the bottom was a degree 1, that's a difference of 3 degrees. Your asymptote would be cubic shaped. But parabola is as high as we're going to go. All right, so let's verify what we just found in that last example. Let's graph the problem. Let's graph our asymptote, and let's see that this 2x squared is really the EBA. Let's do that. All right, so we had 2x cubed minus 4x squared. All right, so 2x, try x again, cubed. All right, minus 4x squared plus 3. And we're going to divide by, what is it, x minus 2. Okay, what I'm going to do is I'm going to draw this as a thin line. Okay, I want it thin because I want you to be able to see the detail as it's getting closer and closer. And it's hard to see if it's thick. So I'm going to go down a line. And I just press left once, go to OK, and it'll make it a thin blue line. Asymptote is 2x squared. So I'll put that. I'm going to do that dotted, because that's how we usually do asymptotes. So I'll do it dotted. I have a couple choices. I'm going to do the small dots rather than the bigger dots. Okay, let's do zoom 6 and see what we got. I think I'm going to have to zoom out a little bit for you to see what's happening. You're going to be able to see kind of what's happening on the left, but not so well on the right. So let's set the y max. Let's try about 40. And I think you'll see it a little better. All right, so let me take that. Let's bring it down and make it a little bigger. All right, so if you look closely, that graph in blue, that's what we're going to try to sketch. All right, so it basically towards the ends, as x gets farther away from the origin, say, in this case, really from like 4 on, and even like -2 on, my graph basically traces exactly the path of a parabola. Okay. Can people tell how this part right here and this part are getting closer and closer together? Okay, that's the asymptote. Okay. On the other side, same idea. Those red dots and the blue line are getting closer and closer till finally they're so close it looks like they're right on top of each other. If I could make the dots even smaller, you would see that they're not. But what's weird is in this section. Okay? The graph does not continue like a parabola in that section. All of a sudden, it kind of drops off right at your vertical asymptote, which is, if I just put this in, make it a little smaller. Vertical asymptote is right there, right at 2. So the curve for the left part of the parabola kind of stays right along the parabolic asymptote till it gets close to that line, and then it's going to stay close to the linear asymptote. Same thing here. It's like this part is sandwiched in that V-shaped section right there. It's stuck between the two asymptotes. Okay, so that's what we're gonna try to sketch by hand, but I think we've shown that the 2x squared is a good asymptote. Okay, that's the EBA. So any questions on how we supported the result we found in the last example? Right, so let's try to make a sketch. First thing I would do here is always get the asymptotes, because that gives you a good idea of how to do it. How about, Brooke, how do I find the vertical asymptotes?
You set the bottom equal to 0.
Perfect, set the bottom equal to 0. X equals 2. Okay. From the sketch, we already knew that, but let's put that in again. Okay, so here's my vertical. And I'll put that in right there. Now, the other thing I'm going to do is sketch my parabolic asymptote. So what I'm basically going to do is I'm going to sketch that. I'm going to change it to a dotted line after I sketch it. And then I'm going to erase the section that's kind of near the vertical asymptote, because I know it's not just going to go through and connect. It's going to all of a sudden drop off like that. And same thing on the other side. It's going to kind of go like that. All right, so let's do that. How about Destiny? When x is 0, what do I get for y? 0, 0. Yep. Dan, when x is 1, what do I get for y? 2. So when x is 1, I get 2. Keep in mind, my y-axis is going by 2's here. And remember, parabolas are symmetric. All right, let's do a couple more points. When x is 2, Tyler, what do I get when x is 2?
8.
Yep, so 2, 8. So right about there. And Tyler, other Tyler, what about when x is 3?
That'd be 18.
18. All right, so 3, 18, negative 3. Okay, hopefully I've got those at the right spots. Okay, now I'm going to draw my parabola the best I can, but I'm going to make it dotted after I do it. Okay, so have your parabola kind of go like that. Okay, make it dotted so we know that it's an asymptote. And remember that in this section around here, it's not going to connect, okay, because it can't cross that vertical line. All right, so now we'll use the calculator and check some values out on the table. All right, so I think I already have it typed in. So let's check just before 2. Just before 2, I'm at negative 300. Okay, so I'm like way down here. Just after 2, I'm up at positive 300. So to the right of my asymptote, way up here. Now, the question is kind of how that turn is going to happen near the origin. So what I might want to do is get a couple more points. Let's get 0. So 0, negative 1.5, about right there. Let's get 1. 1, negative 1. Remember, my y-axis goes by 2's, that's why it looks like that. All right, so I think in this section, it's pretty much going to look, staying very close, starting to get further away. A little curve in there. And then getting closer to that asymptote. Okay, now the other section, what I think I'm going to do is I'm going to plug in like 2.5 just to kind of figure out one more point. 2.5, I'm at 18.5. So maybe somewhere right around there. So I know I'm trapped in this V section right there. I can't get outside of that. But I also have to stay very close to each dotted line, the green and the black. So it has to do something kind of like this. And let me make that red because that's what I was doing my sketch in. And there's your sketch. Okay. You're not seeing on my graph as much of this top part because my y-axis here stops at 20. If I stop this graph at 20, then it would look more like this one. Okay, you'd only see a very, very small section of that U shape. That part is that part right there. Any questions on it? Okay, so that's the toughest graph that really we're going to do today. Everything else is going to be easier than that. Okay, so let's try this one. So first of all, they're asking me to find the end behavior asymptote. Why can I even do that here? What makes this a problem that the EBA is applicable? Yep.
The high section
Right, the degree in the top is bigger than the degree in the bottom. So that makes it the appropriate kind of problem to even consider the EBA. Vertical asymptotes, we'll do that like we always do in a minute. And then we'll sketch a graph. Okay, let's start with the EBA. Okay, so to find the EBA, Tanner, I know I have to do division, but could I do synthetic here? Yeah. So you remember what the form has to be for the denominator? Someone, I think, said it earlier. The denominator has to be, this is quadratic. You can't have a quadratic denominator for synthetic. At least I didn't teach you how to do it that way. But, what does it have to be, Felipe? It's got to be linear. So this is a problem where you can't use synthetic. It doesn't work. All right, so we'll just write it out. As always, be careful if you're missing any terms. We have 2x cubed, 7x squared, 0x minus 4. Okay, let's divide it out and see what happens. Abby, what's 2x cubed divided by x squared? 2x. Yep, 2x. Notice the degree on that. The degrees are only going to go down from there. So this asymptote already isn't as bad as the last one. It does have a square in it. So multiply the 2x back out, and you got to do it to everything. Okay. So we get 2x cubed plus 4x squared minus 6x. 2x cubed minus 2x cubed, that's gone. What's 7x squared minus 4x squared?
Yeah.
Root?
3x squared.
Yep, 3x squared. And now 0 minus 6. What does that give me? Abby?
6
plus 6x. Okay, and now we can bring down our last term. And let's finish up. What's 3x squared divided by x squared? Yep, plus 3. And if you want the EBA, you're done. That's the EBA. If you want the remainder, which this problem didn't ask for, you would keep going. Does anybody want me to finish it up in case I did ask for the remainder, or you think we could do that? People feel okay with remainder? Okay. You just multiply the 3 back out to everything, and then subtract your columns. Okay, so there's your EBA. What kind of shape is that? About, Ariana, what kind of shape is 2x plus 3?
Linear.
Yeah, it's going to be linear, but is it going to be horizontal?
Yeah.
Well, think about this. It's basically like this, right? That's what the 2x plus 3 is. What's the slope in 2x plus 3?
2.
So if something has a slope of 2, Could it be horizontal? No, because horizontal is a slope of 0. Okay, so in this case, the asymptote's not as bad. It's not as simple as horizontal, but it's not as bad as a parabola. It's on a diagonal. Okay, so we'll graph our line. Put your y-intercept. Use rise over run. Get a couple points. And draw your asymptote. Okay, probably about like that. Okay, so there's your slant. Now the other thing we want to look for is the vertical asymptotes. Okay, so set the denominator equal to 0. If we're lucky, it'll factor. And then we won't have to do anything else. If not, we'll use quadratic formula. All right, so set that equal to 0. And can anybody think of two numbers that multiply to give you 3 and subtract to give you 2? I think that's factorable, Devin?
3 and -1.
Yeah, so we have x, we've got a 3, he said a +3 and a -1. Let's double check it. X squared minus x plus 3x, 2x. Perfect. So we get 2 vertical asymptotes. And now we'll sketch those. Okay. Once we have all the asymptotes, then we'll just check the behavior on each side of -3 and 1. Alright, so -3, 1. So when we sketch this, our graph isn't going to cross any dotted lines at all. Okay? So think of those dotted lines as boundaries that your curves can get closer and closer to, but they can't go through. Alright. So now, just because the calculator can do the table faster than I can by hand, I'm going to type it in. All right, so we've got 2x cubed plus 7x squared minus 4, and divide by x squared plus 2x minus 3. Okay. Can somebody give me a value that is just to the left of that asymptote? Would be a number we could plug in that's just to the left of that. Ruth?
Negative 3.001.
Negative 3.001. Okay. Way up. Okay, up over 12,000. So, up there. What would be a value that's to the right of -3, just a little bigger than -3? Brooke?
2.99.
Can you say it one more time?
2.99.
Careful, we're dealing with -3. So if like on a number line, if -3 was here and that was 0, 2.99 would be like
negative
way over there.
2.9.
Yeah, let's do -2.99. Way down at -1,000 something. Okay, it's way down here. Okay, now our next asymptote is at 1. Tyler, what would be a value that's a little smaller than 1?
0.99.
Sure, and a little bigger than 1?
1.01.
Okay, so to the left, we're way down, to the right, way up. Okay, way down, way up. All right, so let's start with the section on the left. So I know that I'm going to have some kind of curve that has to stay very close to that line, and then slowly it's going to start to get further away from it. But it also has to stay very close to the slant as it starts to head to the left. Okay, so that has to stay here, but slowly it's going to start to move away from it. And the two have to connect, and they just connect as a nice smooth curve. So that's what your left part looks like. The middle part, all I know right now is you're going to have something that comes down and gets closer and closer to the dotted line. Something else that comes down getting closer and closer. I really want to know what's happening up at the top. So I'm going to try -1 and 0, just to get a couple more points. So -1, we're at -1/4. So we're going to go through that point. And 0, we are at 1.3. So we're going to go through that point. So we can see how, in the middle section, how it's going to be trapped by all 3 lines. Okay. It's going to try to go up, move away from the vertical, but then it's stuck at the slant. And then it can't keep going because the other vertical forces it back down. And in that right section, it's kind of like the parabola. You're going to be trapped in that V shape. So it's going to come down and go back up. Okay, remember, all of these continue forever. Okay, let's look at the graph and see how we did. So there's the left section, here's the middle, and you're just seeing a little bit of that top part in your graph. Okay, any question on that one? Okay, so I think that one, the asymptote, is a little bit easier. And because the asymptote is on a diagonal, it's called a slant asymptote. I would expect on the test to probably see something like that. Not as bad as a parabola, not quite as easy as horizontal, it's kind of in the middle. Any question on that one? Okay, so we have 2 questions left. One of them is calculator. There's nothing we need to do except draw a picture on the screen. And the last one we'll do is a word problem. Okay, so let's graph this on the calculator. And I'm doing this to kind of point out something that can happen. So you've got 2x to the 4th plus 7x cubed plus 7x squared plus 2x. And divided by x cubed minus x plus 50. Okay, I'm going to do zoom, just do zoom 6, and let's see what it looks like. Okay, before I even put it up on the screen, what kind of asymptote would you expect here? Look at the degree in the top and the degree in bottom and the difference between them. Yep.
A curved asymptote.
What's the difference in degree?
Degree 1.
Yeah, the difference between the top and the bottom is just 1 degree. So to get a curve, you have to have at least a degree 2 difference or higher. So a degree 1 would be what kind of asymptote?
Slant.
It would be a slant. Wouldn't be as simple as a horizontal. It would be a linear function asymptote. And if I open the graph, you can start to see the slant asymptote. The other part, it's kind of hard to see, but I think this curve starts to level off a little, and it's right in there. Okay, so let's look at that. Is there anything about that graph that looks, I don't know, suspicious, or something like we might want to investigate it a little more? Abby?
It looks like it's flat on the x-axis.
Yeah, it looks like it's pretty flat. So what I'm going to do is I'm going to zoom in exactly where I just put that box. So let's zoom in there and look at that. So that's between -1 and 1 on my y-axis. So I'll put that in first. And on my x-axis, I'm looking between -3 and 2. See if that shows it a little better. All right. So that is a picture of what's in the box up above. Okay, so we took that, we zoomed in. I don't know, I can kind of start, does anyone kind of see something right there a little bit? Kind of, to me, it looks like it's almost going down in that section, and then maybe back up. Okay, it's kind of hard to see, so let's zoom in again. I'll keep my x min and max the same, but this time instead of negative 1 to 1, I'm going to go negative 0.1 to 0.1. So I'm going to zoom in even more on the y-axis. So now we're going to be negative 0.1 to 0.1. Let's see what that looks like. All right. So now that we've zoomed in even more, we can see that. So was it really flat? No. Okay, so the point is, it's not that something was off the screen that you couldn't see. It was right on the screen. It was right in front of you. But you have to zoom in to see it. Okay? Now, by zooming in, you kind of lose what's happening down here, but you gain what's happening in that section. So what we thought was flat really crosses the x-axis 4 times. Okay? So the point here is, don't forget to zoom in and see things that are on the screen, and sometimes you have to zoom out to see things that are off the screen. Okay? Any questions on that one? All right, so last one. Okay, so this says we're dealing with rectangles in this problem, and we're constrained to rectangles that have an area of 200. That's the only kind of rectangles we can use. Rectangles that have an area of 200. We're going to let x be the width, and what I want to do is find a formula for the perimeter. And then after we find a formula for the perimeter, I'm going to ask you what would be the smallest perimeter rectangle you could have that encloses that much area. Okay, so with this problem, what do you think a good approach would be that would help us visualize things a little better? Eventually, we're going to create an equation, but what might we want to do first? Yeah.
Draw a picture.
Yeah, if you're a visual person, I think making a sketch here would be very helpful. So here's our rectangle. What's the area of the rectangle? Yeah, Destiny? 200 square feet. And they tell us one other thing about the rectangle. What else do they tell us that we can label?
The width is x.
The width is x. What's the formula for area of a rectangle? Because we're gonna need that here. Area, yeah, Destiny. Area is length times width. Let's fill in what we know into that formula and just see what happens. Area is 200. My length, I don't know. My width, I'm calling x. So how would I write my length? What would be the length of each side of this rectangle? Dan?
200 over x.
Perfect, 200 over x. And now they want the perimeter of that. So with perimeter, how do I find perimeter of a shape? What do you do? How about Cassandra?
You add all your sides.
Yeah, just add up all the sides. So I'm going to get x plus x, which is 2x, and 200 over x plus 200 over x. We already have a common denominator of x. What's 200 plus 200? Yeah, 400. So there's a formula for my perimeter. Or if you wanted a common denominator is x, and you would have to multiply top and bottom by x on what I just pointed to. So there's a formula for the perimeter. Any question on that? Rue, did you have a question?
No.
No? Okay. So now we've got the perimeter. We want to find the dimensions with the smallest perimeter. As I'm graphing this, what kind of values only make sense here for my width? Or what kind of values, you tell me which ones make sense or which ones don't, either way. Yeah? Positives are the ones that don't make sense?
No, they're the ones that do.
They do make sense, all right. So positives are the ones you want to use. So let's set our window right away. No negatives on the x, no negatives on the y. X max. Well, that's the biggest that the width could possibly be. Is there any limit on how big the width could be? I mean, think about it. You could have a really, really wide and skinny rectangle. You could have something like this. And that could have an area of 200. Right? So is there really any limit? No, you can make it as long and skinny as you want. So x, let's just go up to 40. And then that's going to make the length smaller. It would be 200 divided by 40. If it was exactly 40. For y max, that is my length. Again, we don't really have a limit because depending on what you make x, if you make x really small, like make x 0.01, 200 divided by 0.01, it's like 20,000. So the length could also be pretty high. Let's just try 40 to start. Okay, let's graph it and see what we got. All right, so we've got 2x squared plus 400 divided by x. Now remember, we're looking for something with a smallest perimeter. So hopefully, when I draw this, we're going to have a minimum somewhere. Okay, let's see what I typed in wrong.
You set the y minimum to 40.
Thank you. So that should be 0 and 40. All right, so I don't see anything on the screen. So first thing I'm going to do is just check, make sure I typed everything right. 2x squared plus 400 over x. Okay, that looks fine. Next, I'm going to go to my table, and I'm going to look at some values and see where we're at. Well, we can't do 0. Width of 0 wouldn't make sense. That's a divide by 0. You just can't do it. When x is 2, we're up at 204. So I'm way off the screen from where I was. All right, so we gotta set our y values a lot higher. Let's try setting this up at, what was the first one? 204? All right, let's try 250. At least now we'll see something. Perfect. And now, does it look like there's a minimum there somewhere? Yeah. Okay, there's a minimum, right? Right there. It was there. Ow. Hold on. All right, so here's our minimum. Right there. And all we have to do is do second calc minimum, and that's going to tell me the minimum for the x. So we're finding the minimum width at the moment. So second calc minimum. Pick a point. If you can, go to the left. Go to the right. Okay, that looks good. I think the minimum will be trapped somewhere in between. And the minimum width is 14.14. Okay, so for my width, 14.14. And what was the formula for the length? How did you label the length on the rectangle? Yeah? 200 over x. So 200 divided by 14.14. Let's see what that comes out to. 200 divided by 14.14. 14.14. those are the dimensions of the shape with a minimum perimeter that would enclose an area of 200 square feet. So what shape is your fence? And I think we've come to this conclusion a couple times. Yeah,
Square.
it's a square. It would be a square. Great. Any questions on that one? All right. Okay, so homework tonight, it's on 235, and it's 38 to 43, 45 to 47, 51, 52, 55, 62, and 63. Tomorrow we will do section 4.3, whole section, we'll finish that up. We'll have our test on Friday. Don't forget that that's the last test of the term, so anything you gotta make up, make sure you come see me before Friday after school. I'll be here tomorrow. I'll be here early in the morning. Just let me know.